The reason why intermolecular forces are important is that they affect the properties of molecules. So the properties of liquids are affected by intermolecular forces. If we look at boiling point or vapor pressure, what we see is that the stronger the IMFs, the more attraction the particles have for each other, and it's harder for them to escape into the vapor phase. And what this means is that they're going to have a very low vapor pressure because they're attracted. They don't want to escape into the vapor phase. Some of them will, a few of them will, but not very many. If the IMFs are weaker, it's going to vaporize more easily because they're not as attracted to each other. They escape to the vapor phase easier, and therefore the boiling point here is going to be lower because it's easier to make them boil, to make them vaporize. These particles here, stronger IMFs, mean that the boiling point will be higher. It's harder to make, because in order to make something boil or vaporize, you have to pull them all apart. So you have to break all of those intermolecular forces. Stronger forces, harder to pull apart, higher boiling point. So for each pair, identify the key intermolecular force in each substance, and that means the strongest intermolecular force that it has, because that will determine its boiling point. And select the substance with the higher boiling point, which will have the lower vapor pressure, which means you're going to select the substance with the stronger intermolecular forces. So stop your recording and go through and try to figure these out. You might have to draw them. I did, and then label the strongest IMF, and then figure out which one of each pair has a stronger IMF, and the stronger IMF is going to have the higher boiling point. And then turn it back on and check and see how you did. Okay, so for A, magnesium chloride is ionic, so it has an ion dipole force when it's put into water. That's the strongest IMF. And then PCl3 is polar because it is unsymmetrical. It has a trigonal pyramidal geometry, so it's unsymmetrical. So it's polar. It has dipole-dipole IMF. And ion dipole is stronger, so it has a higher boiling point. Okay, so looking at B, NH2 can hydrogen bond. So that makes hydrogen bonding IMFs. And CH3F is polar. It has a fluorine, but the fluorine is not attached to the hydrogen, so it cannot hydrogen bond. It has dipole IMFs, and hydrogen bonding is stronger, so CH3NH2 has a higher boiling point. So for the next one, for C, they both have OHs. OH here, OH here. They can both hydrogen bond. However, this guy here has a higher molar mass. So while they both have hydrogen bonding, they also both have dispersion. And this one's going to have stronger dispersion because it has more carbons, higher molar mass. So it has a higher boiling point. Not by much, though. Okay, these next two, they are also isomers. They both have 6 carbons with hydrogens. In the first one, all the carbons are in a straight chain. And over here, the carbons are rearranged so that there is branching. So with branching, so they're both dispersion forces. CH is considered nonpolar when they're all grouped together. So it's nonpolar, it gets dispersion. Also dispersion and nonpolar. So they both have the same forces, but this one has more branching, so it's going to have weaker dispersion IMFs. And weaker forces mean the boiling point will be lower, So the straight chain will have a higher boiling point. Again, for each pair, identify the key forces and select the substance with the higher boiling point, stronger IMFs. Okay, they both have dipole forces. They're both polar, but this one is more polar, so it's got a higher boiling point. Hydrogen bonding has stronger IMFs, so it has a higher boiling point than the polar molecule, which just has dipole forces. For C, they both have dispersion, but 3 carbons is more than 2 carbons, so higher molar mass and larger molecule means it's going to have a higher boiling point. Surface tension is also really affected by intermolecular forces. Remember that surface tension is where the molecules all stick to each other, and they would rather stick to each other than the air, and that forms this sort of bubble that we see that happens when water bubbles together. Stronger intermolecular forces mean higher surface tension. So in the case of water, we see that water has pretty high surface tension compared to other liquids. And the highest surface tension is mercury, liquid mercury, because its forces of attraction are metallic bonding, which are much, much stronger than even hydrogen bonding or any other IMF. Something called capillary action or capillarity is what happens when a liquid, usually water, sticks to the sides of a tube. And this is what happens when we see water form a meniscus, which is that little dip that happens in the middle when we read water in like a graduated cylinder. We call this a wetting liquid, and it happens because glass is made of silicon hydroxide, and it can hydrogen bond to the water. So this tiny little attraction between the water and the glass is what forms this meniscus. So the glass surface, if it's pure glass, it can make hydrogen bonds. They're not very strong, but it can do this, especially with water. If you've got a liquid that's called a non-wetting liquid, something like mercury that does not want a hydrogen bond, it will actually do this and bubble away from the glass because it will be more attracted, it will not be attracted to the glass. Viscosity, the definition, is resistance to flow, so things that are really highly viscous are hard to pour, like syrup, like maple syrup, or thick motor oil or something like that. Stronger the IMFs, the higher the viscosity. So if you've got something like maple syrup or honey that has hydrogen bonds, it's going to have a really high viscosity and be hard to pour. Water is easily pourable even though it has hydrogen bonds because the molecules are so tiny.